Hello, everybody. Yes, bad pun. Pardon me, that's the only Czech or Slovak I know. As the title says, this talk will be about Alloy, and it's going to be one of those talks that started out with a question. Dumb or not, I'll leave that to you. But I asked myself around Christmas, can I just plug Grafana Alloy into the OTel Demo? And what this question means and what it implies, we will discover throughout this talk. I also prepared the demonstration of how I went over this task. But first, let's get the introduction out of the way. I'm Daniel. I'm a DevRel and CNCF astronaut from Germany, where I work for Netways Web Services. We are a German managed service provider, providing services like Kubernetes, databases, S3, but we also host a public cloud and managed apps like Nextcloud, just ready off the shelf for you to consume. And normally I'm especially interested in GitOps and infrastructure as code, but after I deploy way too many resources and applications automatically, I would also like to observe and monitor them automated and well enough. So that's why I got into OpenTelemetry this winter. I started to redo my home lab, another thing I really enjoy doing in my free time. And this time I decided it was time for some observability. I didn't want to learn about things not working 1 week later because my partner started to complain they didn't work. I also build small web apps, and yeah, that's mostly what I'm up to in my free time, especially in winter when I can't go out. So, the last 2 points, tinkering with my home lab and OpenTelemetry, led me to doing this talk. And let me say up front, I still consider myself a beginner of OpenTelemetry, and that's why I would like to recap a bit of what is OpenTelemetry. Both for me and for you, this is labeled an introductory talk, so maybe somebody hasn't heard about OpenTelemetry yet or doesn't know the specifics. So let's go over them real quick. What is OpenTelemetry? OpenTelemetry is an open observability standard, an open observability framework, which provides different components ranging from tooling to APIs to SDKs, all of which serve the case to collect, process, and export telemetry data. OpenTelemetry is vendor neutral and standardized. That means no matter which of the components you touch or you implement, they will behave the same in a foreseeable, predictable way. And they're vendor neutral, so they support lots of different exporters, receivers, storage backends, both enterprisey like Datadog, as well as open source, like for example Prometheus, Loki, Thanos, whatever. I really like the OpenTelemetry project for the fact, among others, that it tracks and communicates its progress very transparently, because that helps in implementing. You don't have to guess, is this supported, is this not supported? They give you a clear state for each component. We will see this later on. That might help you in making a decision to implement some parts of the OpenTelemetry ecosystem or not. And that brings us to the different components that exist, the different things the OpenTelemetry framework defines. And the most important thing, of course, are the signals, because without signals, we don't get any observability, right? So what can we observe? We can observe metrics. Those are just measurements captured at runtime of our applications or infrastructure services. And in OpenTelemetry, they consist of the measurement itself, the time it was captured, and associated metadata. That could be labels extracted from the app where the metrics were measured, but also stuff added later through a processor, for example. The types of this measurement can be either a counter, which always ever goes up, like the odometer in your cars, an up-down counter, which could represent something like the length of your message queue, which might go up and down, a gauge, something like the level of fuel in your car, or a histogram, which is very interesting if you have questions like, how many of my server requests are terminated below 1 second or have a runtime of less than a second? As you can see on the right-hand side, as I just mentioned, the OpenTelemetry project communicates clearly the state of the different components and the languages it supports as a project effort. Of course, there are additional community-maintained SDKs for additional programming languages, and there are special interest groups and so on. But the languages which are officially supported are C++, C#, Golang, Java, JavaScript, PHP, Python, Rust, Erlang, Elixir, Ruby, and Swift. And we will see the status for each of those and the components throughout the next slide. So as you can see, metrics are quite stable. The rewrite in Rust hasn't been finished yet, apparently. This is the same for all signals, I can tell you already. And there are a few languages in development stage still, so not ready for production use or advised against using them in production. The next signal then would be logs. That's all about writing it down and reading it when the time comes, right? Logs are basically just a timestamp text record. And what I like about OpenTelemetry's approach to logs is they don't force you to re-implement your logging solution. They just build on top of it. So you can bring whatever logs you have. They can be structured, like JSON formatted logs. They can be semi-structured or completely unstructured, like just your console log, debug 1, debug 2, debug 3. And it will work. So OpenTelemetry will be able to work on top of that and with it. Logs can also be correlated to traces through a mechanism called baggage, which is metadata which can be passed between different OTel signals. And as you can see here, the status between the SDKs and different languages is a bit more mixed. You got a few more languages still in development state. Golang is also still in beta. And mainly the enterprise-y languages, a little bit older or earlier mainstream languages like C++, C#, Java, PHP are in a stable state. The third signal fully supported by OpenTelemetry as of today would be traces. And traces can give you a big picture of what's happening within your infrastructure and application, as in they trace the flow of program logic throughout different components in your systems. That could be microservices, that could be different parts of your systems like databases, message queues, and so on. And they do so by establishing a parent-child or maybe sibling relation between so-called trace spans. And what we have here is one such span, but very simplified. So this is not the actual representation within the OpenTelemetry protocol. It just boils down to what's most interesting on first glance, and that would be the name, the context. We can see here it has a trace ID. That might be the same for multiple spans, right? Because we can establish a hierarchy within a trace. It has a span ID, and then we already see it also has a parent ID. That means it is a child span to some other span. So something else happened within the same trace before this span was recorded or observed. It has a start time and end time, and again, it has metadata in forms of attributes, which can give additional information on where, why this was happening, in which context. Traces are the most stable signal. That might be part to the fact that OpenTelemetry itself is a merger of the two projects, Open Tracing and Open Sensors. So traces were there first. And again, Rust is still busy with its rewrite. And there's also a fourth signal, which was added to the OpenTelemetry protocol in version 1.3, but is still marked as unstable in general, and that's profiles. And profiles record dynamic information about the behavior and performance of your application code at runtime, and you can use this signal or these gathered signals to then render them into those flame graphs you might have seen, where you can break down which parts of your application, down to the line of code in some cases, takes how long to process a request, what are the memory resources needed for that, do I run into some loops here and there and it takes ages or longer than it needs. So this is where profiling can be tremendously important in the future, in my opinion, but we're not there quite yet. Now, you somehow need to generate all those signals, right? They won't just fall out of your source code. To quote the OpenTelemetry documentation, for a system to be observable, it must be instrumented. That is, code from the system's components must emit signals, such as traces, metrics, logs, and then you can go on and collect them somewhere else. More on that on the next slide. So right now, there are basically two different approaches to instrumenting your application code or infrastructure code. And one of them is code-based, where you use the SDKs available for the various languages and instrument your code properly, which would give you deeper insights, rich telemetry from within the application itself, because you can basically set the context and the information you want the signals to contain yourself. If that's too much work, or the SDK for your language of choice is still in a development state, or for whatever other reason, more often than not, there's a zero-code approach, where OpenTelemetry provides you with the tools needed to get an outside look on your application and instrument it for you, basically at runtime. Of course, you won't get as deep an insight as with code-based telemetry and instrumentation, but it's great for getting started or can't modify the application yourselves, talking about like vendor-provided binaries you just put in your systems and run, stuff like that. And as mentioned before, those SDKs and APIs needed for instrumentation are available for various languages, more than just the officially supported ones. There are community efforts all over the place. And there are several vendors downstream who also provide their own instrumentation solutions. Now we know how to emit those things, and we might already have an idea of where to store them in some kind of time series database or log aggregation solution. But how do we collect them? Our applications won't just send them to the storage solutions automatically. And this is where the core of it all comes into play, which is called OTel Collector. And the OTel Collector receives, processes, and exports telemetry data. That means it can take in data from various sources, be it Prometheus, applications themselves, Datadog, many other solutions. It can then process them, batch them, sample them, relabel them, enrich them with additional information, or leave out information that's too verbose or just not needed, and then pass it on to the storage backends, because the OTel project doesn't really care for storage. They made the decision to not think about storing data. They just want to produce telemetry data and process it. The OTel Collector is a great way to reduce overhead of operating multiple signal-specific agents or collectors. So instead of scraping metrics, then passing metrics on through an agent to a storage and doing the same 2 or 3 more times for traces and logs, you can just plug the OTel Collector in the middle. It is able to deal with all those signal types and pass it on to the respective backends. How it does that, we will see in the demo. And in addition, it takes care of housekeeping, basically. So it can batch your telemetry data, I already mentioned that. It can retry failed forwarding to the storage backends for you. Maybe there's a short-term outage in your data center or something. It can encrypt telemetry data, and so on. Here's a more detailed graphic of basically the same thing. This is what the OTel Collector could look like, all the things in the middle. So data comes in from various sources, Jaeger, Prometheus, whatever. Then there run some processes in defined pipelines, and then it emits the results to storage backends, like, again, Jaeger or Prometheus, or an OTLP conformance storage solution. Now we covered basically the concepts, the building blocks of the OpenTelemetry ecosystem, but you can, of course, extend them. That's the great thing about open source, right? As we heard in the keynote, you can contribute back, you can make your own thing if you don't want to complain that the solution doesn't exist. You can basically stand on the shoulders of giants. And the OpenTelemetry project has an official name and concept for that, and that's OTel distributions. And distributions are defined as customized versions of an OTel component, so basically a wrapper around one of the OpenTelemetry repositories containing various components. And those distributions normally introduce additional capabilities, for example, authentication or other means of config management, or they change some of the default settings because you don't want to configure the 500 instances of your OpenTelemetry collector within your organization every time something changes. So you want to do this from the start, bootstrap it with it. Or you want to add vendor-specific receivers or exporters, deal with a specific kind of metric format differently than the OTel collector would do. So all these would be good reasons to think about your own OTel distribution. And this brings us to Grafana Alloy, which is the name of the talk. What a coincidence. Which is such an OTel collector distribution, meaning that it is a wrapper around the existing OTel collector. Grafana Alloy is open source, like most of the software published by Grafana Labs, and it was announced at GrafanaCon 2024. GrafanaCon 2025 was last month. Beginning of May. So yeah, almost exactly a month ago. So this means the project is now 1 year old. It's in a stable version. 1.9 just came out on Tuesday, I think, or Monday. And as I said, it is a wrapper around the OpenTelemetry collector. It has built-in Prometheus optimizations, so many things you would need Prometheus for to scrape data, Alloy can do for you, substituting Prometheus basically. And it aims at being a big tent collector for a multitude of observability solutions. That's a recurring theme with Grafana. They also host their own podcast, right, called Grafana Big Tent, where they try to bring a multitude of possible observability solutions and practices under the same roof to centralize them. And as mentioned when discussing distributions, Grafana Alloy does exactly that. So Grafana decided probably to write Alloy because they wanted to see remote configuration possibilities, secret management, including HashiCorp Vault support, sharding and clustering, and live debugging capabilities. These are some of the features Alloy has, and some of them we will see in the demo later on. But that's basically the 101, the elevator pitch. But it's open source, so it's not really a pitch. The good news is, if you want to start using Alloy, you can get rid of YAML. The bad news is, they bring their own DSL. So you're stuck with something different. I'm not the biggest fan of DSLs, but again, maybe a good news after the bad news, it's very similar to HCL, HashiCorp Configuration Language. So if you've ever written a bit of Terraform, you will feel quite confident and comfortable real fast. Same as HCL, it consists of blocks, attributes, and expressions, and as most DSLs, because that's one of the primary reasons to create DSLs, it comes with a standard library of utility functions you can use in your configuration to create configuration dynamically, calculate or evaluate attributes dynamically, things like that. Because the Grafana engineers thought, we put this burden of creating a new DSL and putting it on our users. Alloy also supports the conversion of YAML-based OpenTelemetry collector configuration. So you can run Alloy using an OTel collector config right away. We will see that. But you can also convert it. As of version 1.9, there's a convert command, and there's also a validate command, so you can make sure that your resulting Alloy configuration is sound, at least logically. And I think that might help in case you want to migrate. This is what the DSL looks like. What I did here is on the right-hand side, you see a very simple, minimal part of the OTel collector configuration in YAML, basically just defining the receivers of the OTel collector for gRPC and HTTP OTel endpoints. OTLP endpoints. And on the left-hand side, you see the same in Alloy DSL. It might seem a lot more verbose, but that's just because it's a different format, right? Which comes with its ups and downs. And I want to highlight some of those. So first of all, as I already mentioned, the Alloy DSL is made up of blocks. And those blocks define the receivers, exporters, processors, as you do in YAML for the OTel collector config. Then those blocks can be nested, so nested YAML objects would become nested blocks. Here, for example, for the gRPC and HTTP endpoints, and they just allow you to logically group certain configuration settings that belong or go together, right? Those blocks then can contain attributes, arguments which are required or optional, and they can be either fixed values, strings, bools, numbers, or they can be evaluated dynamically, as I mentioned earlier. So this is where Alloy's standard library comes into play. In this example, in the top here, I read from an environment variable and concatenate it with the port. So we have both string concatenation and function call in the same attribute evaluation. And down here, this is how the Alloy DSL references other components within our Alloy config. Because as we will see later in the demo, the way you build the pipelines, the way you define your pipelines within the OTel collector is a bit different. So there's a lot of referencing going on. And this is how you would do it. Again, this is exactly the same way as you would do it in HashiCorp language. You have like the namespace and the component name followed by the label you gave it when defining it. I already mentioned components here and there. Components are basically just the building blocks for OTel pipelines. There's already a large official library of components maintained by Grafana. Often those are the different teams working on where those blocks belong or those components belong. So most of the components tasked with doing stuff regarding Loki are maintained by the Loki people or Loki engineers, Baylor, Team Baylor, and so on. So that makes sense, I think. And normally each component does a single task. So it either receives data, so it's the equivalent to a receiver in the OTel collector configuration. It exports data, the equivalent to an exporter, or it manipulates data. So that could be a connector or processor or something like that. And each component consists of arguments, which you use to configure your components, and outputs. And those outputs is what can be referenced. So that's something, you can think of it like public attributes, public variables. The outputs are something that you can reference from other components, and this is how you build your pipelines at the end of the day, or reuse values that you might have used somewhere else already. Yeah, and with all this groundwork and basics, I want to get to the more practical part of the talk, because it's demo time. I just want to have this one last slide before I jump into my demo to establish the scenery, right? So the setup will be the official OTel demo, which consists of a microservice architecture which forms a web shop. We will see that in a moment. And all those microservices are instrumented, some with all three kinds of signals, some with one or two. And the OTel collector collects all these metrics and passes them on to Jaeger in the case of traces, or OpenSearch in the case of logs, or Prometheus in the case of metrics. And then you get Grafana and a lot of pre-built dashboards so you can look at what you're actually collecting. And when I started out with OpenTelemetry and Alloy, I wanted to play with all of this, and then I learned about the distribution concept and was like, wait a minute. When Alloy is an OpenTelemetry collector distribution, and distributions claim to be a wrapper around the real thing, right? Can I just plug in Alloy, rip out the OTel collector, and things still work? For me, that was just a case of trying to learn the Alloy DSL and see what's possible as of today. That was in winter, so now there's a lot more things we can do. And that's the journey I want to redo with you now. So let's go over here. I think this should be readable. Thumbs up, thumbs down, not readable? Is it the coloring or the size? Okay, so maybe, let me see, theme. Maybe I got another one. Maybe not. This looks gruesome, but it should be better. I mean, it says high contrast. Let's leave it at that. So what we have here is the OTel demo. We will use the Docker Compose minimal way to bring it up, because honestly, compose file with like 900 lines is long enough for me for a demo. I won't be doing much typing. I prepared Git branches. I will check them out and show you what I changed when I did this initially. And then we will rather have a look at what does work, what doesn't work, what does it look like in Grafana, and so on, because I think that's more of a takeaway. So by default, that's already running here as well. You can see the whole demo with all its containers. And one of those containers is the OTel collector down here. This is already running, provisioned with this Docker Compose file. And we have this OTel collector config. This is without any changes on my side. And what this looks like here is we get this web shop. We can buy telescopes because it's the OpenTelemetry project, right? I'll just click around, so we might generate some more data, but there's already data in the backend. And this data then gets forwarded. So I can now, for example, look at the proxy. That's easy because there will always data be there. And we can see some traces got collected. We can also look in the demo dashboard. Same front-end proxy service here. We see logs coming in. We also see data points coming in, and so on. All this works out of the box. You just provision the OTel demo. Now, the first step is the most brutal one, because what I'm going to do is I'm gonna switch to one. And this branch is fittingly called Alloy drop-in, because all I did here is I changed the image from the OTel collector image to the Alloy image. And I set a few command flags. Those are needed to use this plugin mode where I can still use the OTel collector config, right? So we define the listening address to see the live debugging UI eventually, which is one of the features of Alloy. We tell Alloy to run in the OTel collector config format instead of utilizing its own DSL. And we point it towards the existing OTel config, which looks like this, by the way. We have a few receivers, a few exporters, a few processors, and then down here, the pipeline definitions. Okay, now let's restart, and I got make commands for that to clean up properly. Let's restart the container. It still goes under the same name, so the wiring works all the same. All our instrumented applications will just keep pushing telemetry data to the OTel collector, just that it isn't the OTel collector anymore, but Alloy instead. So this started, and if I say docker logs OTel collector, we see lots of errors down here. The log messages are quite verbose, so it tells us decoding receivers, error, unknown type Redis, for ID Redis, and it even tells us what the valid values look like. So these are the receivers currently supported by Alloy. And apparently neither Redis as a receiver nor OpenSearch as an exporter are supported. So what did I do as a next step? Well, naturally, I used the same configuration on the Docker side, but thinned down the OTel config. So you can see in here there's no, it's still there. The checkout didn't work? Ah, yeah, I did a -C. Thank you. Good eyes. Here we go. Muscle memory, yeah? Now if we look here in the top, yeah, so the receivers, there's no more Redis. There's a lot of other receivers are gone actually because some of those are just not supported by Alloy yet, but we still got our OTLP receiver, so all the OpenTelemetry native data still gets pushed and processed by Alloy now. We also got rid of the OpenSearch exporter, which also means, unfortunately, that for the time being, our logs only end up in the debug log. They don't really get exported to anywhere else, which also means that we won't see them in Grafana anymore. We'll fix that later, but first, let's see what happens if I restart Alloy again. And again, I'll do. Okay. Well, a step forward is a step forward. It's a different error. This time it complains about a component not existing or being. Wait, but that's a strange error. Or being out of. Or being out of scope. And we have to scroll up a bit, actually. This is just the stack trace of the config it tried to render. This is the case because within Alloy, similar to OTel, some components are stable, some are not stable. And yeah, we defined a component to be used, the exported debug component, that is still in an experimental state. So this still doesn't work. Let's move on. This time we didn't change anything in the OTel config, or I didn't change anything in the OTel config, but instead I added this flag here, stability level experimental. So we need to tell Alloy it's okay, you're not as old as the OTel collector, you just celebrated your first birthday. Let's say experimental is fine. We still love you, or don't. That's up to you to decide. Meanwhile, I killed my terminal, okay. So let's restart Alloy. Log it, yet another error. This time it's a config cycle, and the reason for that is that Alloy builds its pipeline representations internally a bit differently to the OTel collector. So in the OTel collector, when you define those pipelines, you can see there's a memory limiter in the traces pipeline, there's a memory limiter in the metrics pipeline, in the logs pipeline, and so on. And OpenTelemetry will implicitly create standalone objects or instantiations of these processes for each kind of metric or each pipeline it ends up being used in. Alloy just creates directed acyclic graphs and thus can detect cycles, because within Alloy's representation, this is indeed a cycle in the case of the traces pipeline, because traces go into a few different things, get turned into metrics, and then a cycle starts appearing. So again, we need to butcher our config. We need to check out, cycles, this one. And our pipelines got even smaller. However, if I restart it now, it should work, but at what cost? Yeah, here we can see it's running. It's getting data, and this is the first time we can take a look at the debugging UI. We can see our components here, they're healthy. We get an in-depth view where we can see that the different inputs we delivered, and we get those graphs, which is quite nice because we can see in real time which data is processed where. Just give it a few seconds. Here we go. So blue would be traces, green would be logs, orange would be metrics, and so on. And we can see the flow of this data. However, as I said, we butchered the pipelines. It's basically, it's like 30 to 40% of what the original OTel demo is. So let's switch to the Alloy config format, and then I'll be done, I'll promise. This one changed a lot, actually. So you can see here the reference to the OTel config format is left. We mounted a config.alloy file in addition to the others. I didn't change anything else because this is where our now actually Alloy DSL config is located at. And we should have a quick look at this config, which is in here. You can see its syntax highlighted. So there is an Alloy extension for VS Code you can use as of today already. And this is what this might look like in Alloy. I won't go into detail here now. I explained the basics of the DSL earlier, but it is possible. I also added Loki to the deployment instead of OpenSearch, because as we saw earlier, OpenSearch is not supported, so logs go to Loki now. I adjusted the dashboard definitions in Grafana, and what I'm doing now is I'm going to restart the whole stack to make sure that no data is preserved. This might take a few moments. And this way we can check. If we see all data in all the different panels in our Grafana dashboard, we successfully managed to substitute the OTel collector with Alloy, and it just works. Let's see. We're still waiting for one of the services. Da-da-da. That takes a long, long time. Here we go. Okay. So let's refresh Alloy. We see the pipeline graph is a bit bigger now because we can actually reuse some of the pipelines that were present earlier but not possible to use with the OTel config and Alloy are now doable again. We see the website is working. I'll just click around a bit to emit traffic and stuff. We see traces end up in Jaeger or not. Might take a few more seconds. Yeah, here we go. And we also see data in the dashboard. And this means it should see logs. Okay, maybe that's the demo gods, or I mismemorized the makefile thing. So apparently it didn't restart and didn't reprovision. But just trust me, let alone the Grafana debugging UI tells me at least the pipelines within Alloy are healthy, they are working as expected. And everything else I blame on the demo gods and my lacking skills, I guess. Yeah. So what did we learn? What did we just see? What did I even do here with all the Git branches and stuff? Well, we saw that Alloy is an OTel collector distribution. That means, by definition, it should allow me to process telemetry signals the same way or a similar way with the same behavior as the OTel collector. And it does indeed. We can build pipelines. We can live debug them. We can use either YAML, so you can start by migrating your existing configurations over, or you can rewrite them in Alloy DSL. The configuration is component-based, which makes a lot of sense, actually. So for me, actually, I was starting out with OpenTelemetry and Alloy at the same time. It was easier to make sense of the Alloy configuration once I had it written down than the YAML, where I had to cross-reference everything because pipelines were always or only defined towards the very end. And it comes with a few nice built-in features, of which I couldn't really show you much today, but they are there. Feel free to talk to me on the hallway track later on. Just to summarize, you can live debug. I showed you a bit of that. You can also get debug logs, filter things in the web UI as they come in, and so on. You can get external configuration capabilities, clustering, compatibility, and so on. And with that, it's time to thank you. I hope it was at least a bit interesting or funny, or a way to have a break after lunch, I guess. Here's all the links that might be interesting. There's also a QR code for the slides. The demo is available on my GitHub repository. You can just go through the branches as I did. There's a README explaining it as well. I linked the Alloy docs. There's my website and my social links in case you have any questions. And I would be very happy about feedback. This is the first time I gave this talk. So scan the QR code. Only takes 30 seconds. I would be very happy. Thanks.
Thank you, Daniel. We now have 2 questions from Slido. Let's go to the first one.
Okay, first question, I just read it. Let me go here. From your point of view, what are the main reasons to use Alloy instead of OTel collector contrib? So one reason I see quite often on the Grafana Slack, for example, where I hang out a lot and people come with their use cases and problems that arise out of them, is Alloy can do lots of things because they are built in, because Grafana wanted them to be built in. One example would be you can scrape Docker containers without deploying cAdvisor and Alloy or any other scraping solution, because Alloy has cAdvisor actually built in. It just knows how to scrape Docker containers out of the box. Same with many other Prometheus exporters. So it can just export things from many things. You would normally put a Prometheus exporter next to them and then scrape that one. So Alloy can do that for you. Another reason is some of the more enterprisey features which you would have to build on top solutions for other OTel collectors, like, for example, secret management. I actually had a longer demo plan where I would upload the configuration into S3 and then just reference it in a minimal stub config file locally, providing S3 credentials. So that could be cool. You could have centralized configuration and just have it rolled out from all your Alloy agents where it fits automatically, stuff like that. So definitely more of the enterprisey side of things, but also some just quality of life features, I would say. I hope that answers that question. And the second one, do you use Alloy in production? Do you use rest of Grafana stack? We don't use Alloy. We use pretty much the whole rest of the Grafana stack, self-hosted, to observe, monitor, and maintain our public cloud. So we use Grafana, we use Jaeger, we also use Falco and so on, which is not from Grafana, I get it, but we use Loki. And some of those parts we also use in our products, right? So we allow our clients with a one-click solution to get a Grafana, Loki, and Prometheus to monitor their clusters themselves if they don't trust us or if they want to have visibility into these parts of their managed offerings as well. So yeah, we are heavy users of Grafana. We only use their open source product line, so we're not in Grafana Cloud or Enterprise or anything. But we do use most parts of the stack.